Today, you will learn about understanding psychrometric charts. I will explain the basics of psychrometric charts, so it will also be a review. Under the theme of utilizing psychrometric charts, I would like to explain how to read the changes in the air plotted on the psychrometric charts and how to calculate equipment capacities. Air conditioning systems in psychrometric charts. To calculate capacities of air conditioners, assume the following conditions. Conditions of the air conditioner. For room conditions, assume that during the summer the temperature is 26 degrees Celsius and the humidity is 50%, while during the winter the temperature is 22 degrees Celsius and the humidity is 40%. For outdoor conditions, assume that during the summer the temperature is 35 degrees Celsius and the humidity is 60%, while during the winter the temperature is 0 degrees Celsius and the humidity is 40%. In respect to the air conditioning cooling load, assume that the sensible heat is 48 kilowatts, while the latent heat is 4 kilowatts. In respect to the air conditioning heating load, assume that the sensible heat is 27 kilowatts. The amount of outdoor air intake is 2000 cmh. In addition, also assume that the fan static pressure is 800 pascals, the fan efficiency is 0.7, the temperatures of the cool water are 7 degrees Celsius at the inlet and 12 degrees Celsius at the outlet. The temperatures of the hot water are 50 degrees Celsius at the inlet and 45 degrees Celsius at the outlet. So let's begin with cooling. Let's plot the design conditions. The position of circled number 1 shows the status of outdoor air, while the number 2 shows the status of room air. Let's calculate the sensible heat factor. From the room conditions plotted at point 2, draw a line for the sensible heat factor. The SHF is determined by dividing the sensible heat variation by the total heat variation. The total heat variation is the sum of the sensible heat variation plus the latent heat variation. The result is 0.92. If you connect the standard point and the point indicating the obtained sensible factor 0.92, you can draw the coordinate line for the sensible heat factor. Draw a parallel line to this SHF line starting from point 2. Let's set the outlet air temperature. For general air conditioning, the outlet air temperature difference is often set at 10 degrees Celsius, so, this time, we also set the difference at 10 degrees Celsius and the outlet air temperature at 16 degrees Celsius. Set the outlet air temperature to be on the coordinate line of the sensible heat factor on the chart. Here, the outlet air temperature is set after the outlet air temperature difference was set at 10 degrees Celsius. The outlet air temperature difference is often set at 10 degrees Celsius but may not be necessarily set so. The relative humidity of the air at the cooling coil outlet is set to the value within the range of 85% and 95%. Let's calculate the supply airflow. The supply airflow is calculated using the sensible heat load and the outlet air temperature difference. multiply by 3,600 and divide the result by the sum of the density multiplied by the specific heat multiplied by the temperature difference. According to the indicated conditions, the supply airflow is 14,400 cmh. Let's plot the outlet air point of the cooling coil. There are two ways to determine the outlet air point of the cooling air point. One way is to set the position where the air comes out as the point of the cooling coil. A relevant standard set by the Ministry of Land, Infrastructure, Transport and Tourism is used. The other way is to take the fan heat generation into account. For general air conditioning, approximately 1 degree Celsius is often considered. Here, we select the way to determine the increased temperature obtained through calculation. For example, manufacturers of industrial air conditioners use this way if fans are required to have a higher static pressure. To determine the increased temperature, divide the fan static pressure by the sum of the density multiplied by the static pressure efficiency multiplied by 1,000. The result of the calculation is 1 degree Celsius. Although the temperature increases, the variation is not found on the corresponding coordinate line of the sensible heat ratio. The humidity and enthalpy of the air doesn't change, but only the temperature changes, so the point of the air can only be plotted in the direction of the temperature axis. If the fan static pressure is higher, you should consider an increased temperature because the degree of the temperature rise is greater. You should set the relative humidity of the outlet air of the cooling coil to be 95% or lower. Let's plot the inlet air point of the cooling coil. The inlet air point of the cooling coil is where the outdoor air and the return air mix with each other. Determine the mixing point according to the conditions of the outdoor air, the return air, and the airflow. The calculated enthalpy at the mixing point is 58.2. The mixing point is positioned at a point on the coordinate line 58.2 of enthalpy connecting the outdoor air point to the return air point. Let's calculate the coolability of the cooling coil. The coolability of the cooling coil is calculated from the difference between the inlet air enthalpy and outlet air enthalpy. Determine the outlet air enthalpy of the cooling coil by viewing the psychrometric chart. The coolability is determined by multiplying the airflow by the air density by the enthalpy difference and dividing the obtained result by 3,600. The result of the calculation is 82.6 kilowatts. Let's connect the inlet air point and the outlet air point. I will briefly introduce how the air conditioning load is represented on the psychrometric charts. At first, I will explain about the room air conditioning load. The room air conditioning load is determined according to the difference between the enthalpy values 2 and 5. The calculation result is 52.8 kilowatts. The enthalpy is used for calculation. This result therefore corresponds to a quantity of total heat exchange. This value is almost the same as the total heat load under the conditions of air conditioning. Next, I will explain the outdoor air conditioning load. To calculate the outdoor air conditioning load, two different airflow rates are used based on the enthalpy difference to be used. When you use the enthalpy difference between the outdoor air enthalpy and the room enthalpy, you use outdoor air flow rates. On the other hand, when you use the enthalpy difference between the mixing point enthalpy and the room enthalpy, you use supply air flow rates. Be sure not to mistake what each point on the psychrometric chart represents in the air conditioning system. The coolability is represented by the sum of the room air conditioning load, the outdoor air conditioning load, and the heat load. You can calculate these loads, but you can directly read them if you use the psychrometric charts. Next, I will explain heating. Let's plot the design conditions. The position of number 1 shows the status of the outdoor air, while number 2 shows the status of the room air. Let's set the outlet air temperature. The supply airflow was already calculated when you learned about cooling. Let's calculate the outlet air temperature difference according to the supply airflow rate and the room heating air conditioning load. The outlet air temperature difference can be calculated by dividing the sensible heat load by the airflow rate, the air density, and the specific heat. The result of the calculation is approximately 6 degrees Celsius. The outlet airflow temperature difference is 28 degrees Celsius. When you consider heating, you do not take the latent heat load into account. The values of absolute humidity at the outlet air point and the room air point are the same, but only the temperature changes. In short, the sensible heat factor is 1. Let's plot the mixing point. The mixing point is the inlet air point of the heating coil. Determine the mixing point according to the conditions of the outdoor air and return air in the airflow. The calculated enthalpy of the mixing point is 34.1. The mixing point is positioned at a point on the coordinate line 34.1 of enthalpy connecting the outdoor air point to the return air point. When you consider heating, determine the temperature of the mixing point because the temperature of the mixing point is generally used. You can read the temperature of the mixing point to be 18.9 degrees Celsius. Let's plot the outlet air point of the heating coil. Outlet points of heating coils depend on the humidification methods used. While paying attention to the changes in the condition of the air depending on the humidification methods used, let's determine the outlet air point. For heating coils, the values of humidity of the inlet air point are the same as that of the outlet air point. If the water humidification method is considered, the enthalpy is constant. The enthalpy of the coil outlet air is the same as that of the outlet air enthalpy. The point of the absolute humidity, which is the same as the mixing point, is the point of the coil outlet air. If the steam humidification method is considered, the temperature is constant. The temperature of the coil outlet air is the same as that of the outlet air temperature. The point of the absolute humidity, which is the same as the mixing point, is the point of the coil outlet air. The temperature of the water humidification reads as 29.8 degrees Celsius, while that of the steam humidification reads as 28 degrees Celsius, which is the same as the outlet air temperature. Let's calculate the heating coil capacity. You can calculate the heating coil capacity by using either the temperature difference or the enthalpy difference. The enthalpy difference is calculated the same way as cooling coils are. Here we will calculate the capacity using the temperature difference. The heating capacity is determined by multiplying the airflow by the air density by the specific heat by the temperature difference and dividing the result by 3,600. For water humidification, the points of the coil inlet air and the coil outlet air are as shown on the slide. Using the difference between the 2 points, calculate the heating capacity. The calculation result is approximately 53 kilowatts. For steam humidification, the point of the coil outlet air is as shown on the slide. Using the difference between the 2 points, calculate the heating capacity. The calculation result is 44 kilowatts. Let's calculate the humidification capacity. The humidification capacity is determined by multiplying the airflow by the air density by the absolute humidity. The absolute humidity difference is the difference between the humidity at the mixing air point and that of the room air point. The calculation result is approximately 14 kilograms per hour. You can see the psychrometric chart on this slide. As a typical example of an industrial air conditioning system, I will explain the basics of calculation of equipment capacities, assuming that the equipment is used for a clean room. In many cases, you can find that heat is generated mainly by manufacturing equipment. Most of the equipment have only sensible heat loads. Air conditioners are operated in cooling mode throughout a year. The example of representative configurations for air conditioning systems includes a combination of outdoor air conditioners and dry coils. Such clean rooms include the following characteristics. 1. Throughout a year, the conditions of room temperature and humidity are consistent. 2. The outdoor air is used to control the dew point temperature of the supply air. It does not load up in the room. 3. The room sensible heat must be treated using dry coils. Now assume that, as air conditioning conditions, throughout a year, the room temperature is 24 degrees Celsius and the room humidity is 50%. To prevent the outdoor air from acting as a room load during summer, the room temperature and humidity of the outdoor air must be adjusted to be the same as those of the room air. But if cooling coils are used, they cannot directly change the room temperature and humidity. Instead, the air with its dew point temperature equal to that of the room temperature must be ventilated so that no humidity loads up in the room. This procedure is called air supply dew point temperature control. If you want to control the temperature, install reheating coils following cooling coils to change the temperature of the supply air. This temperature control is used to adjust the outlet air temperature difference with circular airflow and to air condition a number of rooms with one outdoor air conditioner or one regular air conditioner. During winter, the temperature after humidification must be adjusted to the room dew point temperature. I will show how the air changes depending on humidification methods. The saturation efficiency for humidification can be calculated by dividing the difference after subtracting the absolute humidity before humidification from that after humidification by the difference after subtracting the absolute humidity before humidification from the saturation absolute humidity. Assuming the saturation efficiency to be 70%, calculate the saturation absolute humidity. The result will be approximately 0.0128 kilograms per kilogram. In the case of steam humidification, the condition of the air changes with the dry bulb temperature being constant, so allow the air to change at the temperature equal to the saturation temperature. Heat the outdoor air to approximately 18 degrees Celsius. Vaporize and humidify it until its temperature reaches the supply air dew point temperature. On the other hand, in the case of water humidification, the condition of the air changes with the enthalpy being constant, so the temperature of the humidified air will be higher than the room temperature. As I said earlier, manufacturing plants are usually cooled, so water humidification, therefore, is unsuitable for air conditioning. As reference for humidification, let's consider the two-step humidification method. This method is used when humidification cannot be carried out in one step. For example, when the temperature of the heat source is limited. Set the goal humidity at the same as that set for steam humidification. Assume that the enthalpy is consistent, and determine the saturation absolute humidity. Also assume the saturation efficiency to be 70%. Calculate the absolute humidity before humidification. The result of the calculation is approximately 0.0066 kilograms per kilogram. The point showing the air before humidification is 0.5. Next, assume the absolute humidity after humidification to be 0.0066 kilograms per kilogram and the absolute humidity before humidification to be 0.014 kilograms per kilogram. Calculate the saturation absolute temperature. 0.5 shows the condition of the air before humidification, while 0.6 shows the condition of the air after humidification. The outdoor air is heated shifting from 0.3 to 0.5 and humidified shifting from 0.5 to 0.6. Then it is heated shifting from 0.6 to 0.5 and humidified shifting to 0.6. Thus, the air is humidified through two steps. This process is called the two-step humidification method. For the one-step humidification method, the air is heated to approximately 50 degrees Celsius. For the two-step humidification method, however, the air is heated to approximately 30 degrees Celsius. Dry coils are used to treat sensible heat loads in a room. They lower the temperature but not the absolute humidity. In short, if dry coils are used, drainage water is not produced. The temperature to send water to dry coils, therefore, must be set at the room air dew point temperature or higher. You can find only the change in air temperature on the psychrometric chart. Finally, I will summarize today's explanations. An equipment capacity is the sum of the room load, outdoor load, and fan heat load. If the humidity is controlled, The temperature of the supply air must be lowered to be equal to the room dew point temperature. Air conditioners, therefore, need capacities over the sum of the loads as shown above. The supply airflow is calculated after the outlet air temperature difference is determined based on the room's sensible heat load. You should determine the supply airflow, taking into account the entire balance of air and the number of cycles. Calculate the capacity of coils according to the difference between the enthalpy values before and after the air passes by the coils. If only the temperature changes as seen in heating coils and dry coils, use the specific heat of the air, and calculate the coil capacities according to the temperature difference. The amount of cold or hot water to be provided to the coils can be determined according to coil capacities and the temperature difference of the supply water. If you increase the temperature difference of the supply water, less water is necessary. If you use steam coils for heating coils, determine the steam quantity by using the condensation latent heat of the supply vapor. Calculate humidification capacities according to the difference between the airflow and the absolute humidity difference. This is the end of Understanding Psychrometric Charts, the second section of the practical use of psychrometric charts, calculation of equipment capacity.